is Electromagnetism lesson 10, and we're going to do F equals BIL. So it's the force that acts on a current carrying conductor when it's placed in a magnetic field. So basically, you put a wire near a magnet, it'll experience a force, and it depends on BI and L. So they're all listed below. So F's force measured in newtons, B stands for flux density. You could also say magnetic field strength or magnetic flux density. That's measured in Tesla, which is a capital T. I is current measured in amps, and L is length measured in meters. So what I've got is 4 example questions, relatively straightforward ones, and then I've got a really difficult extension question for question number 5, where you'll have to pull in knowledge from other areas. So if you want to start with this question using that equation, and I'll take you through the answer. All right, let's go. So number 1, a wire of length 0.771 meters has a current of 8.45 amps flowing through it. The wire is placed at right angles to a magnetic field with a flux density of 1.75 Tesla. Calculate the force on the wire. So relatively straightforward. We just write F equals BIL. So let's just put the numbers in. So magnetic flux density 1.75 times the current 8.45 times the length 0.771. So that gives us a force that's equal to 11.4 newtons. Just so you know, 1.75 Tesla is an outrageously high magnetic field strength. The MRI scanners in hospitals are, they're obviously really strong magnets. They're approximately between 0.5 and 1. So 1.75 is not entirely realistic. I'm not sure where you get magnetic field strengths that high. So if you get a really outrageous, in an exam, what I'm saying is if you get a really outrageous answer, like you get, 10,000 Tesla, you might want to look at your working out again. Anyway, let's look at the next one. Right, here's number 2. So if you want to attempt this, and then I'll take you through the answers. So in this one, a wire of length 0.324 meters is placed at right angles to a magnetic field of flux density 0.134 Tesla. The wire feels a force of 0.292 newtons. This time we're calculating current. So F equals BIL. And it's quite simple to rearrange. So we need the current. So we need to make I the subject. So to rearrange it, what we need to do is we need to get rid of the B and the L. So they're multiplied, so it's times B times L. So to move it to the other side, we just do the opposite. So the opposite of timesing is obviously dividing. So we divide on the other side, so it's F divided by BL. And that will give us the current. Then we just need to put our numbers in. So the force is 0.292 newtons divided by flux density 0.134 times the length 0.324. Put that in your calculator. 6.7 newtons. All right, let's do number 3. So I'm going to pause and have a go at this one. So number 3, a wire has a current of 8.1 amps flowing through it. The wire is placed at right angles to a magnetic field with a flux density of 0.96 Tesla, and it feels a force of 2.35 newtons. Calculate the length of the wire. So straightforward again. So it's F equals BIL. And this time we need to make the length L the subject of the formula. So we've got a times B times I. So to move it to the other side of the equation, we just do the opposite of timesing. So we're going to divide. So that's the force F divided by BI. And that will give us the length. So let's put the numbers in. So it's 2.35 newtons divided by flux density 0.96 times the current 8.1 amps. So that gives us a length of 0.3 meters. All right, so one more straightforward one, and then we'll try the extension question. So here's number 4, if you want to attempt that one. So number 4, a wire of length 0.424 meters has a current of 3.75 amps flowing through it. The wire is placed at right angles to a magnetic field and feels a force of 2.88 newtons. Calculate the magnetic flux density. So again, F equals BIL. And this time we need to make B, which is the magnetic flux density, the subject of the formula. So we need to get rid of a times I and times L. So the opposite of that is obviously dividing on the other side. So F divided by IL. And that gives us magnetic flux density. Then it's just a matter of putting the numbers in. So the force, 2.88. divided by current, which is 3.75, times the length, 0.424. Put that in your calculator. And that gives us 1.8 Tesla, which, although that's a high magnetic flux density, it's not outside the realms of possibility. Let's move on to the extension question. I'm warning this is very difficult and you will need to pull physics knowledge from different areas. Right, then number 5. So you can pause and have a go at this one. A wire of mass per unit length of 13.5 grams per meter. So that means that a 1 meter length of this wire is 13.5 grams. If you had a 2 meter length, you'd double it to 27 grams. It's suspended in midair using a magnetic field. The length of the wire is 630 millimeters. The wire has a resistance of 15 ohms. A voltage of 0.1 kilovolts is applied across the wire. Calculate the magnetic flux density required to hold the wire in place. So if you weren't sure on this one, as I'm starting to go through it, if it clicks in your head, you might want to pause it and then finish the question off before you check your answer. So essentially, we're going to use F equals BIL to calculate the magnetic flux density B. So we know the length 630 millimeters. The current we don't know, but we can calculate that. And the force we don't know either. So let's get the current first of all. So current, Ohm's law is V over R. You might remember that equation as V equals IR. So V over R, so V is 0.1 kilovolts, so we have to times that by 1,000 because it's kilo, so that'd be 100, divided by a resistance of 15 ohms, so that gives us the current. And the current is 6.67 amps. Okay, right, so the force that's holding it up. Now, if you've got a wire suspended in midair, so try and draw a wire, so there's a wire in midair. The magnetic force is holding it up and it's got to overcome the weight, mg. Remember, weight is mass times gravitational field strength. G being gravitational field strength on the surface of the Earth is 9.8 newtons per kilogram. So the magnetic force has to be equal to the weight. So what we could do is replace this F with mg because they must be equal to each other. So mg equals BIL. Right, so we know gravitational field strength is 9.8. We know the current is 6.67 amps. We know the length. We just need to calculate the mass. So we've got 13.5 grams per meter. So 13.5 grams per meter. I'm going to times that by the length of the wire, which is 630 millimeters. So to get that in meters, you have to divide by 1,000, which is 0.63 meters. And I've written it like that so you can see that the meters actually cancel out. And we end up with 13.5 times 0.63 and it'll give us an answer in grams. So the wire has a mass of 8.5 grams. And then what we need to do with that is obviously convert that into kilograms by dividing by 1,000. So that's 0.0085 kilograms. Right. So now we've got mg equals BIL. We need to rearrange to make B the subject. So to do that, we need to get rid of a times I and a times L on the right hand side. To move them to the other side, we do the opposite and we need to divide by IL instead. So mg divided by IL will give us, oops, didn't mean to do that, will give us the magnetic flux density. Then we just need to put our numbers in. So the mass is 0.0. In fact, let me just make a little bit of room. Get rid of this diagram. Get rid of this. So the mass is 0.0085 multiplied by gravitational field strength, 9.8, divided by the current, which is 6.67 amps, multiplied by the length, which is 0.63 meters. And if you put that in your calculator, 0.02 Tesla. That's rounded up slightly. If you got that, really well done. It's a very difficult question. If you didn't get it but you could follow it, that's also really good. And if you picked it up halfway through, that's obviously great as well. Anyway, thanks for watching. I hope you found that helpful. Speak to you soon.